Advanced Factoring Methods, Algebra 2, Common Core. So in the previous video, we reviewed some very common factoring methods. Methods that you've learned in previous years that you should have mastered already, but it was kind of a just a refresher, reminder type of video. But now we're going to learn some methods that you may or may not have learned before, and some I'm almost positive you haven't learned before. And then we're going to even expand on that later in class of some challenging with factoring patterns questions. But what we're really focusing on here are factoring with grouping, something I call AC factoring with grouping, and factoring cubes, which are definitely more challenging than the basic trinomial dots GCF factorings, but it's important that you have that strong foundation. So let's take a look. First, we're going to start off with something called factor by grouping. Now, factor by grouping only occurs when you have an even amount of terms. And what you're going to see in this video and in this class to follow is it's always going to be 4 terms. But it is possible to do it with 6 terms and 8 terms and different amounts of terms. And we'll get to that when we get to factoring patterns. But factoring with grouping requires an even amount. Now, it's never just 2, because if we're just 2 terms, then it's simply a greatest common factor question or a dots question. But if you see 4 terms or 6 terms, you want to think about factoring by grouping. Now, as always, we still want to look for that GCF. Is there a greatest common factor? Because a lot of times it starts with that and then it goes into these more advanced methods. But there is no greatest common factor here because this constant does not have an x. Factor by grouping simply is you want to group it into groups of 2. And we can do that by slicing it down the middle. I'm going to group the left 2 and group the right 2. And then what we do is we group them and then we GCF each side. So GCF the left and GCF the right. See, there was no greatest common factor with all 4 terms together, but there is a common factor between the first 2 and the last 2, and that's really what grouping does. So the greatest common factor between the first 2 is x squared, and my quotient is x minus 5. They both have x, the highest exponent I can take out is 2, left with x minus 5. Now the GCF on the right side, now a tip that I'm going to tell you is whatever the sign is of the first term on the right side, that's the sign you want to take out with your GCF. Because I see here I could take out a 4 or a negative 4. Both of these are divided by 4 and negative 4. It's going to be better if I take out a negative 4. And I know that because that's the first sign that I see. And what's left over is a quotient of x minus 5. When I take negative 4 from that, I get x. When I take negative 4 from 20, remember we're doing division. So 20 divided by negative 4 is negative 5. And you may notice something. What we call a common quotient. X minus 5 is the quotient on both sides. That's not a coincidence. That is a requirement for factor by grouping. And it's kind of a nice thing because it checks your work for you halfway through the problem. If you don't get x minus, doesn't have to be x minus 5, but if you don't get a common quotient, if these don't match, something is wrong. And it's possible that it's not factorable or you're doing the problem wrong. So after you do this, then you group the GCFs together and you group the common quotient together. Essentially, we take x minus 5 away from this whole row, and when we take x minus 5 away from the left, we get x squared, and we take it from the right, we get negative 4. Most people don't think of that as a GCF step, but it actually is. But you see that the 2 GCFs combine into a binomial, and the common quotient combines into, but we only write it once. Sometimes people want to write it twice because they see it twice up here. But remember, we factor that out as a single factor, what's left over. So we end up with a double binomial similar to when we factor trinomials and dots. However, we need to examine these binomials closer. Is there a GCF here? Can this be factored? Is it a dots? No. Is there a GCF here? Is it a dots? Yes. X squared minus 4 is a difference of 2 squares, can be factored to x plus 2 and x minus 2. And then, of course, we have the x minus 5. Done. Now, that is factor by grouping. What I want to show you in the next question is how to do that, but then turn it into a solution, which essentially is just if we had this equal to 0, we would turn them into roots. But let's do one more example of it. What is the solution set of the equation? Now, there's a typo on this problem. It's not actually an equation. So do me a favor and do a little edit. Throw an equal 0 on the end. All right, now it's an equation. All right, so we're going to cut it in half, and I'm going to do this work a little bit over here. On the left side, again, take out x squared. We're left with x plus 3. And on the right side, I could take out a negative 4, again, left with a common quotient of x plus 3, still equal to 0. I can group my GCFs together, and that's, again, going to be a difference of 2 squares. And so that's the x plus 2, the x minus 2, the x plus 3 equals 0. But because we're doing a solution here, and we have the equal 0 piece, I want to turn these factors into solutions or roots. And that would be, setting each of them equal to 0, x plus 2 equals 0, x minus 2 equals 0. Sorry. And I think most of you are at the point now where you kind of can tell that that's going to be, negative 2, that's going to be positive 2, and I could write that as plus or minus 2 grouped together. And then the x plus 3 is going to give us negative 3. So we end up with 3 solutions. And it's also helpful, we're going to talk more about this when we get to graph structure, that the highest exponent is 3. That means we will have a maximum of 3 roots. It's possible to have less than that because you could have imaginary, you could have one root with something called a larger multiplicity, but we're going to get into that more. But if you end up with 4 solutions and your highest exponent is x to the third, something's wrong. So that's grouping. It's pretty easy. It's really just cut it in half and GCF, look for dots. All right, next we get to a trinomial, which we did last time. We did basic trinomials. What makes this more advanced is the number in front of x squared. Now, whenever you see a number in front of x squared for a trinomial, as we do always, determine if it's a greatest common factor, because a lot of times it's a GCF, you take it out, and then it's a basic trinomial. But 3 is not a common factor of 5 or negative 2, so there's no GCF. So this is what we call, or at least I call, AC factor by grouping. Notice that after AC, it's factor by grouping. That's what this is, factor by grouping. So we are going to do this method of cut it in half and GCF, but the problem is it's 3 terms. You can't factor by grouping unless you have an even amount of terms. So what we need to do is we need to take this trinomial with 3 terms and stretch it into 4 terms. And we have to do that a very specific way. The way we do that is we actually split the middle term into 2 terms. So the first term is going to stay the same, and the third term is going to, or now the fourth term, last term is going to stay the same. But the middle term, I'm going to split it to 2 terms. And those 2 terms have to add to this middle term, but they multiply to AC. That's why it's called AC factor by grouping, is you have to take your first term and multiply it by your second term. I'm going to take this whole thing, this whole first term times this whole second term. I heard somebody recently call it the eyeglass method because it looks like a pair of eyeglasses if you wear glasses when you circle those. First times last, A times C. And what do they multiply to? 3x squared times negative 2 is negative 6x squared. So I'm looking for 2 things that multiply to AC and add to B. A regular trinomial just multiplies to C, adds to B. But here it multiplies to A times C, adds to B. So what are the things that multiply to negative 6x squared but combine to be positive 5x? And you can think about it a little bit, but I'll save us a little bit of time. It comes out to be positive 6x and negative 1x. They multiply to negative 6, add to positive 5. So they go here. Positive 6x, negative 1x. Now that it's 4 terms, we do the grouping stage. But that's the hardest part, is splitting the middle term into things that add to it but multiply to AC. And so I like to write AC off to the side of the problem and do a little bit of algebra over there. Not like in the problem because I don't want to mess up this flow. All right, now I'm ready. I could do a little grouping. I could take out 3x, get x plus 2. Now here, for the grouping, there's nothing in common, but you need to take something out. And I know I need to take out at least this sign. So when you need to take something, you take out a 1 or a negative 1. And it's going to be negative because I know I want to take out that sign. And it leaves me with the common quotient I need of x plus 2. Group together the GCFs of 3x and negative 1 and pair it with one of the common quotients, x plus 2. 3x minus 1x plus 2. And of course you can multiply this out to confirm that it does multiply back to that. You could always do that with every factoring we do, even this. I could multiply all 3 of these out. It'll come back to this. All right, one more example of how to do this, but this time set equal to 0. And so AC, like I said, I like to write that on the side. It doesn't matter if it's capital or lowercase, would be negative 6x squared again. That's the first times the last. And so it needs to multiply to that, but add this time just to positive 1. So let's see. The first term's not going to change. The last term's not going to change. But the 2 in the middle, this time you need to add to 1. Let's go with a positive 3x and a negative 2x. Multiply to negative 6, add to positive 1. So positive 3x, negative 2x. It actually doesn't matter if you put the negative 2x here and the positive 3x here. As long as they have their signs, you can put these in any spot. Some people like to, maybe pair the 2 with the 2 and the 3 with the 3 because you're going to GCF. It works out either way. You can try it both ways. It's the same. Here I can just take out an x, get 2x plus 3. Here I got to take out something, take out a negative 1, get 2x plus 3. So x minus 1 paired with 2x plus 3. Now I should be keeping these equal to 0 the whole time because it's an equation, not an expression. The x minus 1 equals 0 will give me x equals 1. The 2x plus 3 equals 0 is a little bit of work here. I got to subtract 3 and then divide the 2, so I'll end up with a fraction. Negative 3 over 2 and positive 1. I know this video is running long, and I apologize for that, but there is one more factoring method I want to squeeze in here, and that's factoring perfect cubes. It kind of looks like a difference of two squares. It's a binomial, but they're cubes. So instead of seeing even exponents here, you'll see powers of 3, x to the third, x to the sixth, x to the ninth, things like that. And then instead of square numbers here, you'll see cubes. And the cubes are 1, 8, 27, 64, 125, and they get big fast because this is 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed. Remember, this is 5 times 5 times 5, 5 to the third. That's what these cubes are. They're not as well known to you at this point as squares are, but the first several you should get to know really well. Now, with difference of two squares, this has to be a subtraction, but with cubes, it does not. It could be plus or minus. And there's a couple of different options. Let me see. This next one is minus. So we'll do one with plus, one with minus. There's simply a pattern that you need to remember, and essentially a difference of cubes always factors to a binomial times a trinomial. And that's different than all these other things. Like these are always two binomials, two binomials, two binomials, things like that. Here we're getting a binomial and a trinomial. And it's actually pretty easy once you understand the pattern. The binomial is simply the square root of these pieces. And the square root of x cubed is x, and the square root of the cubed root, of these pieces, the cubed root of 8 is 2, because 2 times 2 times 2 is 8. The sign between them is the sign that you see from the first, from the problem you're factoring. So if this was a minus, this would be a minus. So it's the same sign. I'm going to put an S there. Then we kind of just work with these pieces now for the trinomial. Take your first piece and square it. The middle is times each other. And a thing that I always want to mess up here is I want to do times each other double. Like that pattern when we're squaring a binomial is times each other double. That's not what we're doing here. It's just times each other once, not double. And then you square the back. So it is square the front, square the back. It just times each other, but not doubling, just times each other. The signs that go in here are sometimes what mess people up. I wrote an S to represent same sign. The next sign is opposite. So I'm going to put an O. Because this was positive, now it is negative. And then the last sign, always positive. So we use an acronym SOAP to help us remember these signs that we do same sign, opposite sign, the last one's always positive. And like I said, we just do the cubed root of these pieces to get what goes with here and here. Square it, square the first piece, times each other, but with the opposite sign, and square the second piece. Let me show you one more example. 27x cubed minus 8. So the binomial is going to be just the cubed root of these with the same sign. The cubed root of 27x cubed is 3x. 27, cubed root of 27 is 3, because 3 times 3 times 3. And same sign, cubed root of 8 is 2. And then a trinomial, where I will square the first piece, 9x squared, times each other. Now, times each other right now is negative 6x, but it's the opposite sign of that. Same sign in the binomial, opposite sign for the first sign of the trinomial, and then always positive. And that makes sense because I'm squaring this, and so that'll be a 4. So it's really not bad once you get to know that pattern, but it is a little new. This is the most new factoring style that you've had, so it might take a little practice. But remember SOAP, and we'll practice this more in class. Sorry for the super long video. There's a lot we had to cover this time. See ya.